Alrighty. See, people are starting to move further and further back. Not that scary. I don't think so. Okay, so last couple of lectures we've been talking about how you ask questions of a database. And up till now, we've introduced some basic ideas of relational algebra, and we've talked about SQL. And at least based on some of the posts on Piazza, there was some questions of how exactly you convert all of SQL into extended relational algebra. Now, the secret and the kind of missing bit that I haven't covered up until now is that there is a little bit more to relational algebra than what I've described so far. And what your textbook refers to this as is extended relational algebra. So today, you might remember this picture from a couple of lectures ago. Set relational algebra reads in a bunch of sets and produces a bunch of new sets. Bag relational algebra reads in bags and produces new bags. And I kind of hinted there was this other thing called extended relational algebra that reads in lists, or more generally reads in multiple different types of inputs and produces multiple different types of outputs. So, what have we covered until now? We've covered set relational algebra, and we've kind of described how the various operators of set relational algebra work in a bag relational context. We've also described outer joins. And today, we're going to take this and we're going to finish off our list of relational algebra operators with operators designed specifically to work on lists and operators that kind of extend the basic model of lists and data by allowing us to perform more interesting computations over our inputs. Okay, so let me start off with by asking if there are any questions about anything we've covered or anything else before I dive into things. Okay. So I'm going to start with a what I personally think is one of the simpler operations here, extended projection. So originally, we were talking about projection as being parameterized by a list of attributes. What do you do with that list? Exactly. You give a list of attributes, and all of the attributes that appear in the projection list are the attributes that you keep. Everything else goes away. In extended projection, instead of giving a list of attributes, we're going to instead give a list of expressions, arithmetic or any kind of computation that reads in scalar values and produces a new set of a new scalar value. So, for example, I might have a relation called line item that tells me all of the line items on orders that have been placed. And one thing I might want to do is compute the total of the price of all of the line items that I've sold. So, for example, I might do I might compute the price times some discount attribute. I could also compute the amount of profit that I'm getting on it. Any questions on extended projection? Yeah?
Like, if you change the I next to the line to be capital, so isn't it just one word?
Yeah, sure. I'll do that when I post the slides. Typically, you're going to see line item in this format. It's usually treated as one word. All right, formatting questions aside, any questions on extended projection? Yeah.
Basically making your own columns.
Bingo. You're reading in a bunch of columns and you're producing a bunch of new columns. Question? Yeah.
Is this how we're going to handle aggregation?
Good question. The short version is no, but kind of. So let me ask you this. The old version of projection, where we just have a list of attributes, can I use this to simulate that? In other words, is this a strictly more powerful version of projection, or do I need both? So how would it be possible to implement, let's say, bag projection using this?
Expression.
So the expressions are the attributes of the bag. So what do you mean by set your expression to point to the bag?
Like your expression can only contain the bags that you want.
Are the attributes that
The attributes that you want.
Yeah, so your expression, if you wanted to define an expression, price, or excuse me. So every one of these expressions is assigned to a name. So that's listed here as in terms of the string before the colon. So total colon price times 1 minus discount means produce a new attribute total, and to compute total, evaluate price times 1 minus discount. So if I wanted to do just a regular projection, let's say I wanted to keep price and discount, I could do price colon price and discount colon discount. Okay, so extended projection lets you compute new things. Question, has anyone heard of the term map? As in map reduce or map in a functional context, functional language. Okay, that is exactly what this is. All right. Okay, two other operators, sort and limit. So a sort operator takes in either a bag or a set, and it spits out a bag, set, or list, excuse me, and it spits out a new list. In this case, the order actually matters because the output of the sort operator is going to be sorted on some sort of property. So, for example, if you want to sort on the price attribute, well, you come back with a list that is in sorted order. Limit. The limit operator picks the first n items from a list. Fairly straightforward. Any questions? All right. Random question. What would happen if I if I had a limit operator read in a bag? Yeah.
Would it sort internally first?
Would it sort internally first? So how would it do that? So the limit operator is defined as give me the first n items. So when you say, if I tell you give me the first n items, how would you sort your input? On what attribute?
Well, whatever your calling limit on, so if it's like price or something, you want to sort that in first.
So essentially, yeah, it's up to you is the short version. Limit, as far as SQL is concerned, if you don't have a sort operator in your query, then the order is completely undefined. If you want to sort on the first attribute, great. If you want to sort on some sort of internal property, great. If you want to spit the tuples out in whatever order you like, that's just fine. So basically, limit is defined, but limit does is allowed to. You're allowed to do a limit query on a bag. It's just you can't really expect to get anything meaningful out of it. Okay, so last class we talked about implementing these various operators. So how would you go about implementing a sort operator? Give you a little bit of a more in-depth question. So we talked about iterators. We had open, we had get next, and we had close. Is this something that is sort an operation where I could put all of the computation into get next?
Yeah, you do a bubble sort.
You do bubble sorts. Interesting. So you essentially scan all of the input, find the lowest record, repeat,
Yeah,
repeat. Cute. I'd suggest not doing that. At least it's not BOGO sort. Okay, so you could potentially read in, use get next to just read in successively larger tuples. But in principle, this is not necessarily a great idea. So sort belongs to this class of operators that we refer to as blocking operators. In other words, you can't actually start producing tuples out of a sort operator until you've seen the entire input at least once. So yeah, scanning over the entire input repeatedly is one way to do that. But in just the same way, you could potentially read in all of the tuples in your input and then produce a sorted list and then use that sorted list as essentially as a way to produce new tuples. Okay, does anyone see any problems with this? Yeah? What if all of your data doesn't fit into memory? Well, then you got a problem. You're going to start paging, and anytime Java starts paging, anytime Java, general word of advice, you're probably not going to have to spend too much time optimizing, but one thing that I will tell you is that whatever Java's heap size is, assume you have half of that, because as soon as that fills up, you're done. But yeah, as soon as you run out of memory, this starts performing like molasses. Now, I'm going to give you a little bit of a hint and say there are ways around this, but today we don't have time to talk about them. We'll get into them in, I think, 2 or 3 lectures. But this is something to bear in mind. That said, for the purposes of the first project, feel free to take this approach. Your data sizes are going to fit in memory. It's all this approach, in general, is going to be the fastest. Okay, any questions on sort, limit, or extended projection? All right. So, last class, we also briefly talked about aggregation. And there were definitely some questions on how you take aggregation and implement it in terms of relational algebra. Now, before I get to implementing, to expressing aggregation in relational algebra, let's maybe take a little bit of a look at aggregates in general and ask ourselves how we can implement these in a way that's efficient. So, let me back up. So let's say I'm trying to sum up a set of numbers. How much space, how much memory would I need in order to sum up all of those numbers at any one point in time? My working set size. How big a working set do I need to sum up a bunch of numbers? Yeah?
Two variables.
Two variables. What two variables?
The running sum and the current number that you're reading on.
Okay, so I need some sort of number containing my current total, and I need some sort of number, some sort of storage space for whatever number I'm currently looking at. My working set size is constant. Now, can I do something similar for computing the max? Yeah. Min, how about average? Can I do something similar for average? Can I do that with two numbers? Okay, which, so the current tuple, what do I put into this other number?
The counter, see how many, well, can you get the size of the or are you keeping track as
You might need to keep, you assume that you don't have these statistics beforehand.
the second one is to keep track of the size?
Okay, so you'd need the current tuple plus the two variable, you'd need one thing to keep the count and one thing to keep the total, the sum. And then at the very end, you divide the sum by the total and you get the average. Okay, now it turns out that this type of pattern where you keep a small fixed size counter, or possibly several small fixed size counters, occurs a lot in these statistical functions. It doesn't occur in all of them, but it occurs in quite a few of them. And as a consequence, we create the, most databases define aggregates in terms of an operation that kind of looks a little bit like this. So aggregate operators, if you're familiar with functional languages, this sometimes comes up, this sometimes is referred to as a fold. But the basic idea is that you start off with some value, you initialize all of your counters, and then every single tuple that you see, you incorporate it into those counters. And then at the end, you may need to do some extra little bit of computation to produce an actual output. So for example, for sum, what do I do for init? Initialize everything to 0. What do I do for consume? Oh, come on, you just said this. Take in the tuple, you put it into the counter. Finalize, you spit out the value. That's it. So, going back to this model of implementing aggregates, I haven't actually told you what an aggregate looks like in relational algebra, but an aggregate, you read in tuples, and every single tuple you read in, you stick it into the aggregate, and then finally, once you've read everything, you emit what you have. Now you've already answered this, so I expect a unanimous answer here. 1, 2, 3, what's the working set size? Come on. 1, 2, 3. Thank you. Wake up. 1, 2, 3. 2. Okay, good. Need to work on that. Okay. You're running a little bit slower, so let me skip the group work. So the slides are going to have a little bit of just practice exercises that you can try out here. But let's skip these for now. Yeah, let's skip these. And get to one other operator. So in relational algebra, or extended relational algebra, there's an operator called the grouping operator, also represented by a gamma. So the grouping operator looks a lot like projection in that it has a set of attributes, and for every attribute it has either an expression or some sort of aggregate computation. And loosely put, you're going to have a set of grouping attributes, which have just regular expressions, and a set, or sometimes they're just attributes themselves, depending on how you implement it. But you have one set of attributes that represent your group by attributes, and then one set of attributes that represent your aggregate computations. And so, loosely put, for every unique value of your grouping attributes, you compute an aggregate for all tuples that fall into that group. Give you a simple example on the board here. So let's say you have R of A, B, C, D, 1, 2, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what groups would I generate out of this? If I was using that query, sorry. Let's start by what are my grouping attributes? A, B. So I'm going to look at these two columns. What are the unique values of AB? 1, 1, 1, 2, 3, 4. So if I do a group by, this is going to create how many rows? 3. 1, 1, 1, 2, 3, 4. And then if I follow the expression here, it's a typo, that should just be star. The count is going to end up being for this 1, 2, 1, and the sum of the d's for 1, 1, 4, 8. Yeah, and okay. So just as a quick sanity check, what if I give you a group by a grouping operator? What output schema does it give me?
It's a tuple of the items you want to know.
Say again?
It's a tuple of all the columns that you call.
Yeah, all the columns that appear in the group by, the grouping columns and the aggregate columns. Okay, the operation here, or the behavior here, is going to be quite similar to just regular aggregation. You read one tuple in, and if that's the last tuple, great, you emit a tuple. You emit all of your groups. But as long as you still have new tuples, you read one tuple, you figure out which group it goes into, and then you actually put it into that group. So let's actually go through this example following this chart. So we'd keep an internal representation of all of the groups. We encounter this, what do we do? So I read one tuple, and now I need to find out which group that tuple is going into. Which group? One, 2, 3. Wake up. Someone call it out, and then everyone can say this, because I'm not gonna. You're gonna say this at least once. Which group does this tuple fall into? 1, 2, 3. 1, 2. Okay. Do I need to bring coffee or something? I'll do that. Okay, 1, 2. I'm computing 2 aggregates. The count. What do I do with the count? So the count 1 and the sum, I also add that in. And I'll just repeat this process. Every time I encounter a new tuple, I see if I have that group already there. If I do, I'll initialize it all to 0 and incorporate the tuple. 2, it's already there. And I just keep doing that. So, for each of the, yeah.
Why is this on 4? Where's that
Sum of D. So this goes into that group. This goes into that group. Question? So essentially what I'm doing is I'm taking all of these tuples and I'm grouping them by the first few attributes. So in effect I've got 1, 2, 1, 2, 1, 2, 1, 2, 3, 1, 1, 3, 4. And I've got 1, 2, 5, 6, so that falls into this group. And 3, 4, 7, 8. Group 3, 4, tuple 7, 8. Now for each of these, I'm going to squish them all together and produce a single set of numbers. So I'm trying to compute, here I'm trying to compute the count. There are 2 tuples in this group. One tuple in here, one tuple in here. Yeah?
So the ellipses in this are not part of this.
No, ellipses. Oh, the dot, dot, dot?
Yeah.
The dot, dot, dot is just to indicate that there may be more than 2. Does that answer?
Yeah.
Any other questions? Did that address your question?
I understand where the count came from. Where does the sum come from?
So every aggregate operator has an expression as its input. So here I'm computing the sum of D. This attribute is C, this attribute is D. This attribute is C, this attribute is D. So I'm going to take all of the D's, I'm going to sum them up. So 8 here, 4 here, 8 here. Does that address your question? So how much space do I need here? How much space am I using here?
The amount of the input size.
The amount of the input size.
So there's 4 tuples.
4 tuples. Okay. So I split this out to make it a little clearer what's going on. But in practice, you only need to store the counters themselves. So 1, 2, and then whatever those are. Does that change your answer?
Yes, very much.
So
The amount of distinct input.
yeah, the number of groups that you create. So this could potentially also cause a problem, just like sorting. You need to keep around an amount of states that varies based on what kind of, based on your input data. So it's possible, in principle, that this set could get really, really big. In practice, and for the data that you're working with for project 1, it won't. But we'll talk about ways of approaching aggregation that allow you to to avoid running out of memory. Okay, cool. Right. Let's skip. Actually. All right, let's take about 5 minutes and so there's another keyword in SQL, distinct, that we talked about last class. So distinct, what does it do? Removes duplicates. So it gives you it turns a list or a bag into a set. Okay. So once you turn to neighbor on the left or right, and together try and work out how to use the grouping operator to produce to essentially emulate the behavior of distinct. And take about let's call it 4 minutes. A chance to chat. How would I express this in as a relational algebra tree?
I can probably do a pseudocode.
Pseudocode is good.
I was just thinking, like, have you ever, like, when you're pulling in another tuple and you calculate the count, you can just check if C is greater than 1, then don't return this tuple in the output.
If C is greater than 1, then so that's exactly that's, forget that keyword. There is an operator that returns where everything is exactly 1. Distinct returns where it's at least 1. Returns the tuples where there is at least 1 instance. Yep.
Is relational algebra partially set relational algebra?
So basically from now on, I'm going to be talking mostly about extended relational algebra. So if I talk about the operators where it specifically matters, whether you're talking about set or bag relational algebra or extended relational algebra, I'll say so. For the grouping operator, well, okay, so for set relational algebra, this is kind of trivial. So let's say we're working with bags or lists as inputs. So you're onto something there. You're keeping the account or some sort of group by aggregate going on here. So does anyone see a relationship between that query and So mainly what I'm trying to get across here is that the distinct and grouping operators are essentially the same thing. All distinct is doing is essentially a group by, but with no aggregate columns. All right, questions up to this point? Yeah.
Is there any downside to using a hash map to store all your tuples?
So the question is, do you need to use a hash map to store all of your tuples? Replace the word tuples with groups, and my answer is yes. There's a couple of different ways of storing them, but a hash map is going to be the easiest. But in short, you need some data structure that if you give it a group, it can tell you what all of your counters are. Yeah.
In regards to those two statements that do essentially the same thing, this is kind of an ignorant question because I need to read up on RA, but whose RA tree is worse?
So the question is, which RA tree between those two is worse? So let's actually build the RA tree for both of them. So a little more space here. So let's look at the RA tree for the top query. What does that look like? So where do I start?
Start with
Okay, so I start with R. Actually can give you the handy dandy iterator chart. Okay, so I start with R. What's next? Do I have a where clause? Nope. Okay, ignore that. Do I have an aggregate? Nope. Can ignore that. Do I have a having? Again, nope. In fact, the only thing on that entire list that I have is distinct. I can't for the life of me remember what the distinct operator is. So I'm just going to do that. All right, what does this one look like? Where do I start? Yeah. All right, what's next? Where clause? 1, 2, 3. We're going to have to work on this, really. 1, 2, 3.
no.
Much better. Good. Aggregate. Do we have an aggregate?
Yeah, yes.
Yes.
Group by.
Yes, we do. We have a group by. So we have a group by aggregate. Do we have a having? Nope. Select items? Nope. Order by? Nope. In fact, we have pretty much nothing of that entire tree. All right. So we have one relational algebra tree. We have another relational algebra tree.
Just to be a stickler, notation for the group by, like if you use an aggregate, should you notate the
Yeah, so
arguments
this-
you're taking in?
This should be A, B, and then there's no aggregate, so it's just group by A. So you can implement this in a couple of different ways, but basically these two operators are doing exactly the same thing. So to answer your question, no, they're depending on how you implement them, they're identical. There's a question back.
Does that imply projection? Meaning, you don't want the AB column to go.
Yes, so group by does imply, group by could potentially remove columns, yes. But if they get removed, then they're going to get aggregated away. So you're guaranteed to have one tuple for everything in the input. Any other questions? Yeah?
For the distinct tree, will you have to project A and B first select distinct A?
Okay, so yes, you're technically correct that you would have to do that. Although, because of the fact, oh, actually, I'm getting this backwards. You have to do that down here. So technically, I did lie to you. You would have to do that. However, you can detect pretty easily, any query optimizer will be able to detect this, that this operation is doing absolutely nothing. Oh, you're right, it is doing something. Yeah, you're right. Great catch. So in effect, they're still doing the same thing because this grouping operator has to do that projection as well.
So there's an implicit
Yes, so in this case, you're projecting things down and then finding all of the unique values. In this case, you're just taking, there's only two things that you're using to identify the groups. And when you get out of that, you've essentially lost all of the C's and D's because there's nothing, they're not in any of the groups. Okay. So one other thing I want to get to before talking about the project, and that's null values. So you may have noticed throughout, yeah.
I'm confused why you need a project for distinct but not for group by.
So the question is, why do you need the projection for the distinct but not the group by? So the short version is, well, not the short version. So distinct will convert a bag into a set. So in effect, what's happening here is that you're taking attributes A and B, and you are creating groups out of each of them. You're finding all of the groups, and you're computing nothing for it. Normally you'd compute an aggregate here, but in this case, you're not computing anything. You're just finding the groups themselves. But you're basically the group by operator is, in effect, what it's doing is it's creating, it's doing that projection for you. One way to think about it is if you're doing an aggregate, if you're doing a group by aggregate. So let's say I put in something like sum of C in here. So that creates another column in here, sum of C. But if I wanted to, there would be one row in the output of this for every row, for every distinct value in this projection. Does that make sense? Basically, the short version is that a group by aggregate is those two operations plugged together with this additional ability to compute aggregates for each group that it constructs. Does that address your question?
Is this something that you kind of memorize?
Sorry?
Is this something that you kind of memorize and you know like which ones also do different characters? If I see like a new operator.
So projection, so basically the semantics, you can't really define a group by without it having some sort of ability to project columns out. Because if I just did a group by everything, then pretty much everything in my input would produce one row of output. So what I'm trying to get across here is that set projection essentially acts as a grouping operator. This is basically set projection. Distinct plus projection is basically set projection. Distinct plus bag projection, let me be. I told you guys to yell at me if I just used the word projection without set or bag. So distinct plus bag projection gives you set projection. And set projection is essentially a simplified form of the grouping operator. Does that address your question?
Yeah.
Any other questions? All right. All right, so you may have noticed in various places in the slides, there have been some places where there's data that just that's null. So just like in Java, SQL has this notion of a null value for fields where either you don't know something or it just doesn't make sense. So for example, someone who doesn't have a last name or someone who doesn't have a first name. Spock and data are my usual go-to examples. It's probably more applicable to the MS program, but oh. So Spock and data are examples. They don't have a last name. And SQL has this special null value for this. Now, for the most part, null doesn't really do anything too bad. If you try and compute values using null, you get back null. But where it becomes weird, and this is something that that you need to know because this is one of those weirdnesses of databases that doesn't make sense unless you know why it's happening, is when you have a selection predicate. So let's say that I have an officer that doesn't have a rank. Maybe I don't know what their rank is. What would this evaluate to? False. Why do you say false? Null is treated as 0 in a lot of languages. Yeah, so it is normally treated as 0. SQL actually treats null as a special value. What, just intuitively, what should this evaluate to? Not invalid, yes. So SQL uses what's called three-valued Boolean logic. This is really just kind of weird. The idea is that the truth value of an expression can either be true, false, or And a where clause is going to treat every instance of as no. So the where clause is only going to give you the true values. It's not going to give you false or unknown records. And where this really gets weird is when you start thinking about how it interacts with and, or, and not. So if I do, intuitively, what do you think would happen if I do an and of an unknown and false? What is false and unknown? False. Yeah. So if false and anything is always false. Same holds here. Unknown and false is false. What about unknown and true? Yeah. So if I don't know what it is, true and anything is whatever that anything is. So true and unknown is unknown. And the symmetric case also comes up with ors. So unknown or true is always true. Unknown or false is always unknown. And this is the one that gets everyone. Not unknown is unknown. This is the cause of way more bugs that I'd care to describe in my SQL queries, because if you have a null value in your data and you say, you go back to this, so if O.rank is null, then O.rank is both greater than and less than 3. So bear that in mind. That comes up in quite a few places. All right. Yeah, let's cover that. All right. Last bit of relational algebra, and this is something that you're not required to implement, but it is something you're required to know. Is both relational algebra and SQL, something called an outer join. So I have here two relations, one giving me a list of ships with their IDs, and one giving me a list of locations for each ship. Now you'll note that ship 1701 is near a subspace anomaly. Now what happens when there's a ship near a subspace anomaly? It goes poof. So what happens when you have some data that doesn't completely match up? If I were to ask, what is the result of, what is the location of the ship Enterprise? What should I get back? Null or, sorry? Speak up a little. Unknown. Okay, so I would like to get back null or unknown. In practice, what will this query give me? Say again? Nothing. Yeah. There's no result that comes out of there. But you're right. What I would like to get is unknown. So I don't actually want an empty result. I want an unknown. In short, what I'd like to get from the join of these two tables is something where the ship and the location, or the location of the Enterprise, is null. And SQL and relational algebra, or extended relational algebra, give us a way to describe this idea. If we have, refer to them as dangling tuples, if I have a tuple that's in one relation but not the other, I'd still like it to appear in the join result. And this is what's called an outer join. So basically the idea is that if what I normally refer to as a join is an inner join that behaves normally, and I have these three different types of outer joins. And the idea is that if a tuple is in one side but not the other, it'll still appear in the output. Questions? Okay, so either everyone got this, or
The last example, was that an example of a left outer join?
yeah, so that's a left outer join. You'll note the little lines. Those are, by the way, really annoying there's no font that actually has that. Okay. We have about 25 minutes. So I usually like to put in breaks. We're running a little bit behind today, and I really want to cover Project 1. So I apologize. Today I'm just going to go straight through. Okay. Project 1. As of a few hours ago, the checkpoint 1 has been put up. Given that it went up a little bit late, I will probably extend it about a week from the original deadline that was on the syllabus. But today, basically, I'd like to finish up by going over everything that you need to know about Project 1, and without actually giving you all of the code, essentially describe how the reference implementation is implemented. And the idea is, or ideally, if you follow these guidelines, you should be able to replicate the reference implementation and produce something that runs as fast. Okay, so before I get to that, any final questions on relational algebra? Or extended relational algebra? Yeah.
Like in your last example, there were the ship and
That one?
yeah, ship and the location were null. So if you did verify on ship and location, would it even bother to show those null things? Or would it
Okay. So that's a great question. So the question is, what if you have a null value in a group by attribute? Is is a good generalization. So if you have if you have a null value in one of your group by attributes, let's take a look at the syntax that we talked about. So how do we define a group? We define a group by saying everything where the first attribute is equal, everywhere the second attribute is equal. Is null equal to anything? No. Null always produces an unknown if it's used in a comparison. So there is no group that a null value will fall into.
And that applies to students as well. So
That also applies to, okay. That I could not tell you in general. What I will expect is, for the purposes of the project, the answer is yes, that also applies. For the purposes of individual implementations of SQL, I don't believe that's in the spec, so use at your own risk. Null value semantics are, each implementation does something slightly different with them. Yeah?
SQL, does null equal null?
Null equals null is undefined, unknown. Because the short version is null means I don't know what this value is. So I don't know what value A is, I don't know what value B is, I don't know whether those two are equal.
So then is there a way to search for unknowns, like using
So there's a operator called isNull, or a comparator called isNull that says yes if a value is null, no if the value is not null. And you'll see a lot of cases where you'll have data wrapped in kind of a case statement. You'll essentially an if-then-else block where you test to see if something is null, and if it is null, you do something special. But that's a great question. If you're interested in that, check out my webpage. There is a project called Mimir that is precisely targeting this kind of thing. There's this idea called labeled nulls, where every null value has a label on it, and so that you know that two nulls that have the same labels are the same, but two nulls that have different labels, you still can't figure anything out.
So is that like whether the null was generated as part of the data or generated from?
Yeah, exactly. So where the null came from. And there's other ways of approaching this. SQL takes a very, very pessimistic approach to this. So in general, and this irritates me about SQL and a lot of database work in general. In general, the SQL and relational algebra would rather give you no answer than give you an answer that could possibly be wrong. So it takes a very, very pessimistic approach, and so null equals null is always false because it could be true, but you can't take that chance. You'd rather give no answer, you'd rather give false, you'd rather take the pessimistic, I'm not going to do anything approach if there's any chance that something of something being wrong. Does that address your question? There's a question back?
Does null and null return
Null and null, or unknown and unknown. Unknown and unknown returns unknown. Because you don't know. Same thing for or. Any other questions? All right. So, project 1. Okay. So, what will happen? So you've already gotten some experience with the grading system. Essentially, what will happen is that your code will get. All right. Promise me you will not go to sleep. This is basically how to solve project 1. If you go to sleep, it's your own loss. All right. Okay. So. What will happen? Your code will be compiled. Once your code is compiled, it will be invoked on the grading boxes. with basically just like this. This will be all on the slides when they get posted. You're going to get JSQL parser in the class path, and you're going to get your code in the class path. Just like with the Hello World program, it's going to call the class, dubstep.main, and it's going to give you, it will give you a set of, got all of this. It'll compile them, your code, put it in the class path, along with JSQL parser, and you're going to get a couple of arguments on the command line. The first of these arguments will be a directory containing data. So for example, in this case, if it tells you the data directory is /data, then anytime there's a create table statement, we'll get into this in a bit, but the create table statements basically are meant to give you a schema. They don't actually create a table or anything. They're just the standard way of conveying schema information. So if you get a create table line item, that will basically say that there is a file lineitem.dat that lives in the data directory. In addition, you will get on the command line a set of SQL files, and each of these SQL files will contain a combination of create table and select statements. The create table statements give you the schemas, the select statements actually give you the queries that you're being asked to evaluate. You should evaluate the select statements, produce the results, and output them delimited by the pipe character, or vertical bar character. Any questions? Any questions about the interface? Back up to that last slide. Any questions about the expected interface? Yeah.
So you mentioned create table and select statements. We know that create statements first.
Do you know that you're going to get the create table statements first? You will get, yes, the create table statements will always occur before the select statements. Does that? Anything else? Or at least the create table statements will always come before the select statements that they're required for. All right. Okay, high-level workflow. You start with one of these SQL files, one or more of these SQL files. If you get more than one, treat them as if they were just one big file and evaluate statements from them one at a time. The only guarantee I'm going to give you is that there will not be any SQL files that span, or any SQL commands that span multiple files. But essentially the sequence of files, you should process just all of the SQL files as if they're one big, long file. So you will get a set of SQL files, and there will be create table statements and select statements in these. JSQL parser, the documentation will be linked from the, or is linked from the checkpoint description, will give you the ability to process and translate these SQL files into JSQL parser statement objects. Simple way to do this, there's a function on CC JSQL parser, which is the central class, called statement. And you initialize parser with a Java reader, and every time you call statement, it will read the next statement from the file. As soon as there are no more statements to read, it will return null. Questions? Okay, so statement objects, as we talked about a couple lectures ago, can be either create tables, selects, or a handful of others that are not relevant for this project. So each of these is going to get turned into a select or a create table. Let's look at each of these in turn. The create table statement is, it's going to be an instance of JSQL parser's create table class. which means statement instance of create table will return true. And basically what it will tell you is that there is a table that has a set of attributes, and it will tell you what their types are. So in this case, there's a table named players. It has 7 attributes: ID, first name, last name, first season, blah, blah, blah. And it has a data file. All of the data for this schema is located in a CSV file called, a pipe delimited file called players.dat. You don't actually have to create the table. You need to parse this information out and then save it for later. Any questions? Okay. So you take this schema information and you store it. Now, like I said, this the fact that you have a create table players means that there is a file players.dat. Here's some sample data. Will basically contain a set of records, 1 record per line, and 1 field. The fields will be delimited by vertical bar or pipe characters. Vertical bar, aka pipe characters. Now, the other possibility is, when you get a statement, is that it is a select statement. If it is a select statement, then you will either get a union or a plain select. We went through this process 2 classes ago. Go through this whole conversion process. You'll get a relational algebra parse tree by calling the appropriate methods. And let me once again re-emphasize this. Don't try and evaluate the SQL directly. If you do this, you will be in pain. I guarantee it. Do not try and evaluate the SQL directly. Convert it to something simpler like relational algebra before you do that. Questions? Yeah.
Will we be adding more so like extended relational algebra things, or will?
Thank you for yelling at me. Extended relational algebra.
Okay, so then for project 1, it will contain all of the things for project 2 and 3, so we don't have to make it so we can should add things later.
Yep. So project 1, ideally, so project 1 will require, well, actually, thank you for preempting me on this. So we have all of our bag set and extended relational algebra operators. The ones that you will, in practice, need to implement are select, actually cross product for now, rather than join, union, some sort of relation operator or relation scan operator, sort, limit, extended project, and group by. Regular or set projection and bag projection you can get rid of because the extended projection and distinct operators subsume them. The distinct operator is subsumed by the grouping operator, and outer joins are just a pain. You don't need to implement them, and aggregation is subsumed by group by. Does that answer your question? So this is what I would suggest implementing. Again, rather than join, I'm going to use the term join to describe both cross-product and actual joins for now. But for now, you just need to implement cross-product, because we haven't actually covered joins yet, at least not implementation-wise. Okay, questions up to this point? All right. Oh, good. Good progress. Okay, so each of the parts of the select statement, and I showed you that parse tree equivalence earlier, but each part of the select statement translates into a relational algebra operator that builds on the other relational algebra operators that you've encountered up to this point. So, in the case of this query up there, what would I start with? Players, right. So players is what I will get if I call body.getFromItem on the select body. it'll basically give me a table called players, and I need to translate that, create a relational algebra operator, and that forms the basis for my query. Now, moving along, I'll eventually encounter a where operator. In this case, the weight is greater than 200. If there is a where clause, if there is no where clause, this will return null. If there is a where clause, apply a selection to whatever you had before. And finally, you have the select statement, so you'll get the select items, and that gives you your projection. Now, the one thing I want to really heavily emphasize, because it will make life a lot easier when doing this translation, is that every single relational algebra operator is defining a relation or defining an iterator, depending on how you want to implement it. And that means that you can keep this one object and kind of build on it, rather than trying to look at the many different possible cases. So you start off with your input relation, you apply a where clause if necessary, and you apply your projection on top of that. So eventually you'll get this thing converted to a relational algebra tree, and that relational algebra tree includes some information that you're going to have to draw from your schema. So you need to know, for example, that players, you will need to know that the schema of players, for example. Okay, so from that relational algebra expression, you can define a set of iterators. In the reference implementation, there is a separate iterator class and a separate relational algebra class. I've done this mainly for convenience, but there's nothing to stop you from defining them both in the same code base. But essentially, you define your iterators, those iterators read from the data files, and those iterators produce an output. And this is essentially the high-level workflow of the reference implementation. Questions? Okay. Skip that. Right. So then the where clause, the having clause, and each of the expressions that you get in the select targets are going to be in this class called expression. So expression is an interface that defines basically any kind of arithmetic or functional, any kind of scalar valued expression. And the idea is that each of these evaluates down to something called a primitive value. So there are 7 different primitive values. You're going to care about 5 of them. You can ignore timestamp and time values. And this primitive value class also has a bunch of methods to make extracting values out easier. Right. So how do you go from an expression to a primitive value? Now, normally I'd have you implement this yourselves, but given the amount of time that you have available, we're actually going to give a solution to you. There is a class called eval in JSQL parser. And the way this works is that there's a method called eval, and that should be a primitive value. You give it a expression, and it gives you back a primitive value. Now, there's one tricky bit in this, which is that primitive values, columns, which represent inputs from the projections input or the selections input, which represent attributes in the input, the evaluator has no clue what a column should evaluate to, and nor should it. You're going to basically have to extend the evaluator class so that it reads in values from some tuple, and actually you're going to have to implement this translation from column to primitive value, from column to the corresponding attribute referenced by that column. So basically, the way that you use the eval class, you implement this abstract method on the class called eval of column, and then you call eval of expression, and you get back. It essentially does all of the arithmetic for you. Questions? Okay. Last bit. So the last bit is that if you have a join, so I said there's body get from item, body get where, and body get select items that gives you the select project input relation. If you have multiple input relations, they're going to appear in this additional bit called that you can access by calling get joins. Get joins is going to return to you a list of essentially every comma-separated value. This is another case where the fact that the query, where your relational algebra defines operators in relational algebra are just operators, pays off. So you can essentially build up this cross product by just building a cross product of all of the joins that appear in the return value there. So you end up with, well, essentially a projection like that. Okay, we can skip that. I covered it. So with that, basically, that's the workflow on the left. That's that's your guideline. If you have any questions, stop by office hours tomorrow. Originally, it was towards the end of February. Originally, you had 3 weeks. You will have 4 now.